I'm a huge fan of OpenStack Physics, college physics textbook, because it's online, but it doesn't cover everything I want to cover, and it did not cover the real gravitational potential energy. And if we use real gravitational potential energy, we can look at something really fun called escape velocity. So let's imagine this situation. Okay, quick review. So we have this as our gravitational force, which decreases with 1 over r squared, the distance between the centers of the two objects. So as they get further apart, the force decreases. And I showed in a previous video that we could describe the gravitational potential energy for objects moving far from the Earth with this, negative g, mass of the Earth, mass of the object divided by r. And it's a scalar and it's negative, and that's important. We can use this to find out how high an object goes when we throw it. So, but I want to do it first as a Python model using just forces, because then we can play around with it and then we can explore this idea of how high things go. So I'm going to throw a ball with a velocity v1, no air, so don't worry about air, and it's going to go up and it's going to come back down, and we want to find out how high it goes. Okay, so to do that in Python, since we have a non-constant force, we're going to have to break it into short time intervals. But before that, we actually need a better model for gravity, a different version. So I'm actually going to write the gravitational force as a vector, negative g, mass of the Earth, mass, over the magnitude of r squared times r hat. So I'm going to have this as the vector r. It's the position vector from the center of the Earth to the object. And why am I doing that? Well, because if I want to use this gravitational force in more than one direction and let things move around, then I need to do it this way. So these are all scalars. The magnitude of r is a scalar, and I can square that. But then I need to make it back into a vector. So r hat is what's called a unit vector. You don't need to know about it, but that's what it is. And it is a vector with a magnitude 1 pointing in the direction of r. So this turns it back into a vector. Is that cool? Okay, let's go with that. Now, if I break my motion into short time intervals of, let's say, 1 second, if I'm dealing with the Earth, right, how far does an object move in 1 second? It doesn't move that far. So I can assume that the gravitational force is constant. It's not, but I can assume it. Okay, so I can calculate the gravitational force, negative g, me, m over r squared r hat. I'll just write that as, I like that. Okay. And then you can calculate the acceleration, the gravitational force divided by the mass. That you don't have to do that step, but I like to do it because it makes more sense to most people. And then I can update the velocity. And I've done this before, but I'm just letting you know, v2, v1 plus a times delta t. So this says take the velocity at the beginning of the time interval, add this acceleration times delta t to that velocity, and then make that the velocity at the end of the time interval. And then finally, I can use that velocity and update the position, which I'm going to call r. So r2 is r1 plus v2 delta t. And then the object moves, so the gravitational force changes. So it's coming back up here and do it all over again for the next time interval. Time interval, time interval, time interval. Keep doing it. Okay. So I have my Earth. I have my mass of the Earth. I have my radius of the Earth. I have my gravitational constant. This, let's say this mass is 100. It doesn't really matter. I'm going to build this in Python, and we're not using energy yet. We're just doing Python. Okay. We're doing, actually, Newton's second law. So switching to the computer. So I'm using WebVPython like I like to do. And I've already got it loaded up here. So let's just start adding our constants here. G is 6.67 times 10 to the negative 11th. Not going to put the units. ME is 5.97 times 10 to the 24th. The radius is 6.3 times 10 to the 6th. The mass of the object is 100. And I'm going to give this initial velocity a number. I'm going to say V1 equals 1,000. And it could be anything, right? But I'm just going to give it a thing. Now, I do need my velocity as a vector, right? So I'm actually going to give this velocity. I'm going to move it in the x direction. V is going to be the vector v1, 0, 0. And this will make sense later. T equals 0, dt equals 1. And that could be too big of a time interval. It could be too small. We're just going to have to work it out and find out. Now I'm going to go ahead and make my Earth. Earth is an object of type sphere. It's going to be at the origin, vector 0, 0, 0. And it's going to have a radius of r. So sphere is a built-in object in WebVPython, and it will make a three-dimensional sphere. So when I run this, it looks like that. And I can rotate it around with the right-clicking and dragging, and then scroll wheel zooms in and out. But it doesn't look like the Earth. We can fix that with my favorite thing, texture equals textures dot earth. So this puts a wrapper on the sphere that makes it look, it's like a decal to make it look like the Earth. Isn't that nice? Okay, now let's make our object, ball. I'm going to call it a ball. It's also a sphere. I'm going to put it on the surface of the Earth on the x-axis. So the position is going to be vector r, 0, 0. That's the radius of the Earth. And then its radius is going to be r over 20, just so we can see it. I'm going to give it a color yellow. And then I'm going to turn on the trail. Make trail equals true. Let's run that. And there's no ball because it's just right there. Right? It's just zoomed in so you can't see. So there's our ball. Now, did I get the mass? Yeah. Okay. So let's just get to it. I'm going to run this for, let's say, 30 minutes. Yeah. So I'm going to use a time variable to determine how long to run this. And we're going to let the ball move away and back. So t, while t is less than 360, 3600 over 2. So 3600 is 1 hour and seconds. Rate. So rate is a statement. So if we're going to be making an animation, we have to tell it how fast to run the animation. So rate says don't do more than 500 loops every second. And so you can change that number to change the animation rate. Now the next thing I'm going to do is I'm actually going to do a little trick here. R equals ball.pos. So that ball.pos is the vector location of the ball, and I'm going to call it the variable r. It just makes my calculations look better, and it's important to look good, right? Okay, now we can calculate the gravitational force. And this one's, hold on to your horses, negative g times mass of the Earth times m times norm r. So remember I said we need that unit vector r hat. Well, norm r is r hat. It's a built-in function in WebVPython that calculates that for us automatically. And then I'm going to divide by mag r, which is a built-in function that returns the magnitude of a vector. But I need to square that. Now I can calculate the acceleration. Now I can update the velocity. V equals v plus a times dt, just like we showed. And then I can update the position. Now here, I don't want to change r. I want to actually move the ball. So I'm going to move ball.pos as my position. Plus v times et, update time, or you will be stuck in an infinite loop of timeness. That should do it. Let's just see what happens. Oh, something happened. Let's make this go faster. I don't think I had it going fast enough. Let's make this at 3,000. There it goes. Okay, so this blow up stuff is funny. Okay, so what happens is the Earth's not real. The Earth's not there. So as the ball moves back down, it just moves into the Earth. And what happens when r gets very, 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 very small, then the force gets very, very, very large, and then it can just do this weird step thing right here. So it's fine. Let's just make it go a little bit faster so that it doesn't, maybe it doesn't do that. So there it goes. The ball goes up, the ball comes back down, and that's the end. So the question is, how high did it go? Let's make a graph of the distance from the Earth as a function of time. And that's just one way to see this. So making a graph, G1 is graph. I'm not going to give a title. I'm going to give an X title is time in seconds, which is dumb, but I'm going to do it. The Y title is r in meters. And then I'm going to say the width is 400, the height is 200. And then I can plot something that's going to be called a G curve. F1 is a G, and that's just the name I gave it. And I like the color blue. Color equals color dot blue. So down here I want to plot a data point. I'm going to plot F1 dot plot T on the horizontal axis. And then on the vertical axis I want the magnitude of the position. You can't plot a vector. And I just updated the ball, so I'm going to use ball instead of R. So I'm going to have mag ball.pos. Let's run this thing. So there it goes. Okay. So you can see it starts right there. The highest point it gets to is up here at, what's that, 7.86. If I change the initial velocity, it's going to go higher, and we can do all that. But let's do the physics part, which is using work energy to determine how high it will go. Back to the board. Okay, so let's delete all this stuff. So I'm launching my ball right here, and it's going to go up here. V2, R2. And you should, in your mind, say, hey, we're trying to find a new velocity at a new position, and we don't care about time. We should use the work energy principle. And then if you say we should use the work energy principle, you should say, well, what's my system? So my system is going to be the ball plus the earth. Why would you do that? Well, if I have the ball and the earth in my system, then I don't have to worry about this changing gravitational force and find the work done by this gravitational force. Instead, that's part of my system, and it'll have a potential energy. So I'm going to have a kinetic energy of the ball, 1/2 mv squared, and then a potential energy of the system, negative g me m over r. And so I can use both those. Now, I'm going to assume the Earth doesn't move, so I'm just going to have kinetic energy of the ball. Technically, the Earth would move too, but this should work out fine. Okay, so let's put things together. 0 is the change in kinetic energy plus the change in gravitational potential energy. 0 work because there's no work done on my system. This is going to be equal to K2 minus K1 plus U2 minus U1. Now, one of those terms is 0. If I start with the velocity v1, it goes up, and then it starts coming back down. At that point, v2 is 0, the highest point. So I want to find out the position when v2 is 0. So that means k2 is 0. But I can put in my stuff. 0 is equal to 0 minus 1/2 m v1 squared plus negative g, so it's negative g mass of the Earth m over r2, which I'm trying to find, minus a negative, which is going to be plus g mass of the Earth m over r1. And this is an equation that I want to solve for r2. So I'm going to take this term and add it to both sides. It's just running out of room here. So if I add this to both sides, I get, oh, first of all, the mass, this mass cancels. So I get g mass of the Earth over r2 is negative 1/2 v1 squared, the mass canceled, plus g mass of the Earth over r1. Now, it's not pretty to solve. I'm going to solve this in an ugly way. I'm just going to essentially cross multiply, and I can get r2. r2 is equal to g me over all this, negative 1/2 v1 squared plus g me over r1, which is r. Okay, so that's how high it goes. Now let's just go back to Python and see if that is what we can calculate this and compare it to what we did. So switching back to Python, over here at the end, I'm just going to calculate this. So let's calculate R2. I'm going to call it R2 is equal to, now I'm just going to type in my equation right here. I have G times the mass of the Earth divided by negative 0.5 times v1 squared. See, now that's where I get that v1. Right up here, I had v1 as a scalar value, and I use it in a vector. So that way I don't have to retype it. Thinking. Plus g times me over the radius of the Earth. And let's print that out. Print R2 equals. And you say, hey, where's escape velocity? I thought we were doing escape velocity. We are doing escape velocity. Just be calm for a second. Be calm. Okay, so it's going up. It's coming back down. Okay, and so here we got a maximum height of 7.826. I'm just getting that from the graph. There's other ways you could do it. And I print same thing. Okay, so we get the same height using the work energy principle. So that's kind of cool. Okay. Now I do want to show you something. What would happen if I did not launch it this way, but I launched at an angle? How would that change its maximum height? Because the work energy principle is a scalar equation. It doesn't care which way it goes. Well, let's just try it, right? That we built our model so that we can play with it. So let's go up here and edit the initial velocity. So I want to launch at a 45-degree angle, right? But I want to have the same magnitude of velocity. So let's just do it this way: v1 times cosine of be pi over 4. Pi over 4, yeah. And this I'll give it some y velocity, v1 times sine of pi over 4. So, but because I use cosine and sine, it's still the same magnitude of velocity. Okay. So let's see what happens. Notice, oh, that's cool. Look at what it did. See, it went at an angle. And this is the magnitude of the distance away, but still the same thing. It didn't matter which direction you shot it. It still got the same distance away. Okay. So the faster I launch it, the further away it gets. But is it possible? How fast would I have to launch it to get an infinite distance away? That's what we want to do next. So let's go over to the board. And let's look at what if I want R2 to go to infinity. And if it gets an infinite distance away, it escaped. So what changes in our equation over here if R2 is equal to infinity? I'm not going to do this. Let's go back up here to my original equation. Let's just start back over from scratch. And now I want to say not what's the launch velocity and how high does it go. I want to say, I know how high it goes, what's the launch velocity? So I have that same equation. 0 is the final kinetic energy, K2 minus the initial K1 plus U2 minus U1. Now what's different here is that K2 is 0 and U2 is 0. Because if I get an infinite distance away, I'm dividing by an infinity, that goes to 0. So I have 0 is the 0 minus 1/2 m v1 squared. That's 0 minus a negative g mass of the Earth m over the radius of the Earth. And I want to solve for v. This is pretty easy. The mass cancels. m 1/2 v1 squared equals g mass of the Earth over r. v1 is the square root of 2g me over r. So that's how fast I would have to launch it in order to not come back. Let's calculate that. Square root of 2, 6.67 times 10 to the negative 11th times, oh, I'm running out of room here. I'm just going to put it in my calculator. I don't want to run out of room. That's fine. We can do that. Okay. Drop. 2, enter. 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th times 6.3 times 10 to the 6th divided by square root. I get 11243 meters per second. Okay. Let's go back and put that in Python, see what happens. Okay. Going to say, actually, I'm going to write square root of 2 times g times me divided by r. Right, I don't need to calculate it. I'm just put it in like that. And I run this, and it's moving. Oh, I didn't even switch. Sorry. So it's running. Oh, let me show you what I did. All I did was I put in this velocity as a calculation. So let's run it again. There it goes. And there's my position as a function of time. And I only ran it for half an hour. But you'll see right down here, what's the final position? I calculated that as infinity, which is kind of cool, right? That it gives you that infinity, and that's fine. Okay. So now let's make that is the escape velocity. Notice that it depends on the mass of the planet and the size of the planet, or where you're starting from. That does matter. I want to make a graph of the potential energy, the kinetic energy, and the total energy as a function of position. So this is going to be fun. Let's just do this for fun. So up here, let's change everything up. This is going to be R in meters, and this is going to be energy in joules. And then I'm going to call this, I have three things, Fk for the kinetic energy, and it'll be blue. It should be red. Kinetic energy should be red. It's always red. And then I have the potential, Fu, and that's going to be G curve color equals color dot blue. And then I have Fe, which is the total energy, is a G curve, and its color is color dot purple. And I've played around with colors before, and these are the ones that show up the best. Now, I'm also going to do this, I think it's called dot equals true. It leaves a dot, I think. Dot, and it might be marker equals true, but let's just run with it, and if it gives me an error, then we fix it. Okay, so now what I need to do is I need to do some calculations down here. Before I plot stuff, I need to calculate the kinetic energy, so let's do that. So K is 0.5 times M times the velocity squared. So I have the velocity, but I need the magnitude of the velocity, so it's going to be mag V squared. I need the potential energy, U. It's going to be negative G times mass of the Earth times M over R, which is going to be the magnitude of R, again. Energy is a scalar. And then finally, E is just going to be K plus U. Now let's plot those. Fk dot plot. I want to plot the R position, which I'm using R there. It should be ball. That's fine. It'll be fine. It's fine. So let's use the magnitude of R on the horizontal axis. And then this will be the kinetic energy. Fu dot plot is mag R and U. And then Fe dot plot is mag R and E. And let's run this for a longer time. Let's run this for 8. I'm just picking values here, and let's run it faster because no one's got time for that. Let's see what happens. Okay, I like that a lot. I like that a lot. So here's the potential energy as I'm getting further away. The potential energy is increasing, right? We already say you increase potential energy, but it's getting closer to zero. That's why it's important to be negative. The kinetic energy is decreasing, but notice what the total energy is. It's zero. It's zero. So what if I have a total energy of less than zero? So that would be a smaller initial velocity. Let's do that. Let's put the velocity at half of this. So I'm going to multiply by, and let's run it again. And notice what happens. So that dot is equal to true is really nice. So the ball goes away, but it comes back, and it's actually in a little orbit there. Let's make it a little bit faster. Let's make that 0.8. Yeah, that looks nice. Okay, so the kinetic energy is decreasing. This is a plot of position. So as it starts coming closer, then it goes backwards the other way. That's why it's nice to have that dot. You can see that the total energy is less than zero, and it's a bound orbit. If the total energy is greater than zero up here, when it gets an infinite distance away, it's still going to be moving. We calculated the escape velocity so that it would be an infinite distance away and stopped, but it could be going faster. Okay, so but that's how you calculate the escape velocity. It's one of the great uses for this gravitational potential energy, and it's a great chance to play around with graphing and plotting and stuff like that in WebVPython. So again, code for this I'm going to include. Hope you enjoyed that. The end.